Now the next result we're going to discuss is every open subset G of R1, every open subset G of R1 or R we write can be written as G equals to union of IN, where I1, I2, I3 are a finite number or finite number of a countable number of open intervals which are mutually disjoint. That is, IM intersection IN is empty if M is not equals to N. That is a mean. So any open set in R can be expressed as the union of open intervals which are disjoint open intervals. This is what we are going to prove it. We are going to prove this result. Now suppose let us take one element of G. Let X is element of G, then if X is element of union of these, then this X must belong to any one of these I1, I2, I3. That is what we are doing. If X is element of G, then there is an open interval. In more particularly in real line, any open interval is an open ball. An open ball, say B, containing X such that the B must be a subset of G. This is by definition of open sets. Why this is possible is G is an open set and we take one general element of G, so there must be an open interval, and more particularly it is an open ball. Instead of open ball we use the word open interval because in real line we use the word open interval in terms of open ball. So open ball B, say B, that contains X and such that B will be X is element of B and B is a subset of G. This is by the definition of open set because G is open. Let us now define IX denote the largest of all open intervals, the largest open interval containing X such that this IX is a subset of G. Okay, so this G is there, then this X belongs to B and B is a subset of G. This is by the definition of open sets. Now what we take is, let IX denotes there are many open intervals that contains X, among them the largest one, and very important that interval Ix must contain X and should be inside G. Like this is possible. So we are defining that interval as Ix. What is the meaning of Ix? Ix is the largest of all open intervals which contains x and is contained inside G. And this Ix can be not only finite, it may be an unbounded interval also. Ix may be an unbounded interval. It's like say some a comma, like this unbounded interval also possible. Okay. Then what you can do is, then G can be written as, see, every element of G, if a union, I will get G. That is, suppose X is an arbitrary element, like this Y is another element, I find one more interval I, Y. So now G can be written as the union of all these open intervals Ix, where X belongs to G. So if you union all these intervals where this X belongs to G, then I will be getting the G that will be equal to G. Now we are going to prove that this set of all intervals which we do the intersection must be disjoint. Now if X and Y we take it in G, then it should be either these intervals must be same or they are disjoint. This is what we have to prove. Suppose they are not equal, I am going to show that they will be disjoint. Suppose Ix is not equal to Iy, and sorry, we are going to prove by contradiction method. Suppose this, what we are going to prove is either these two intervals are equal or they are disjoint. Now what I am assuming is, suppose they are not equal, and I am assuming the contrary of this, Ix intersection Iy is non-empty, they have some intersection. Then what happens is Ix union Iy would be an union of two open intervals is open interval, be an open interval that is contained in G, which is larger than Ix. See, Ix, Iy, both are subset of G. So union of Ix and Iy, that is also a subset of G, but we just now assume that Ix and Iy, their intersection is non-empty. Therefore, Ix union Iy will be definitely bigger than Ix. But what is the assumption we made here? Ix is the largest open interval containing X and contained inside G. Here what I get, this is an open interval that is larger than Ix, containing X as well as contained inside G. So we are getting a contradiction to what we assumed. We are getting a contradiction to this assumption. This contradicts the definition of Ix just now we discussed. So therefore our assumption is wrong. Therefore these two intervals are either equal or the intersection is what? Empty. Now we are going to show that there is only a finite number or countable number of open intervals. Only finite or countable number of open intervals. Like this intervals only, if I union, then in this union we just consider only finite number of intervals are countable number of intervals, open intervals. So we proved that Ix and Iy, this is properties proved. Now we are going to prove the finiteness or countableness. Now this Ix is an interval, contains x, that's a infinite interval. So definitely an interval will contain a rational number as well as an irrational number, and just now we proved that all these intervals are disjoint. So each interval will contain one rational number. We assume that at least it contains a rational number. So Ix, Iy, Iz, like this, you just collect all the intervals in this collection. Each interval contains one rational number, but already we know that set of all rational number is countable. Set of all rational numbers is countable, and hence definitely there are only finite number of collections or countable number of collections in this union. That we take it from using the properties of rational numbers. So that one we are going to complete here. Finally, each of the set Ix, interval Ix, contains a rational number. Just now we discussed. And since disjoint intervals, all these intervals are disjoint. Since disjoint intervals cannot contain the same rational number, cannot contain the same rational number, and since there are only countably many rational numbers, there are only countably many rational numbers, there cannot be uncountably many mutually disjoint intervals. Yes. So this collection of intervals are either finite or countably infinite. Why? Because each of the interval contains one rational number, we assume it. Then since the number of rational number, each of these intervals cannot contain the same rational number, and further set of all rational numbers is countable. Therefore, if you assume that at least one rational number is inside these intervals, there are only countable number of collection of intervals. So that's what is proved here. So this is only finite number of countable intervals. So already we proved that these intervals are mutually disjoint. So this is what we proved. There cannot be countably infinite number of intervals. Hence the proof. We'll complete like this. So what we proved is these intervals are mutually disjoint and only countable collection is possible. Now the final theorem, very important theorem. Let's consider two metric spaces M1 and M2, rho 2 be metric spaces, and let F is a function from M1 to M2. Then F is continuous on M1 if and only if fns of G, if fns of G is open in M1 whenever G is open in M2. Briefly, F is continuous. F is continuous if and only if the inverse image of every open set is open. This is what we have to prove. This condition is both necessary as well as sufficient condition. So now we are going to prove the necessary parts. The necessary part we are going to prove. So now we are going to assume that F is continuous. Let us assume that the function F is continuous. So now what is the thing is, so now suppose these are two metric spaces, M1 and this is the other metric space, this is M2, and our F is a function from M1 to M2. Now F is continuous, we are assuming here. Now what you have to prove that if suppose you take one open set G here, you take an open set G, now we have to prove that the inverse image of this open set, suppose this is a set, I call this set as what? F inverse of G. The inverse image of this open set is also open. If G is open, you have to prove that F inverse of G is also open, but it is in M1, this is in M2. We have to prove this. This is the necessary part. This condition is necessary for a function to be continuous. If this condition is not satisfied, then the function is not continuous. That's why it is called necessary condition, and it is also sufficient. If this condition is satisfied, that is enough to show that a function is continuous. So now we are going to prove the necessary part. Let us assume that the function f is continuous, and this is what you can imagine. This is G. F inverse of G is somewhere here. G is open. We have to show that F inverse of G is open in M1. Let us assume that F is continuous. Now let G, a subset of M2, be an open subset of M2. Let G be an open subset of M2. We need to prove that F inverse of G is open in M1. We need to show that F inverse of G is open in M1. For this purpose, so to prove that this set is open, to prove that this F inverse of G is open, we want to prove that this set is open. We are going to take a general element, say X, in this set, and we are going to show that there exists an open ball which is completely inside F inverse of G. If this is satisfied, then this is true for every element X in F inverse of G, and hence by the definition of open set, F inverse of G is open. So we need to show that F inverse of G is open in M1. let us assume that there exists an element, say x in fns of g. If x is belong to fns of g, so whatever element we take inside this inverse image, the corresponding images will fall inside g only. So that is what we are going to. Then f of x will belong to what? G. F of x will belong to G somewhere here. So this is f of x. So f of x belong to G. Now f of x belongs to G and G is open in M2. So what you can conclude is, so the open ball B whose center is at f of x with radius some r, definitely this open ball will be inside what? G, because G is an open set. So any element inside that, there will be an open ball which is some radius is possible, which is inside G. And now already one definition is there in section in section 5.3. you can see in section 5.3 we have discussed. It's not needed to write in the examination. So if f is continuous, if and only if the inverse image under the function f of any open ball, say B of f of a colon epsilon about f of a contains an open ball B of a colon delta. This is about the center A. See, if f is continuous, so what happens is, see, if f is continuous, what this definition says is, this is an open ball, suppose, whose center is f of a and this radius is what? Epsilon, and this open ball I name it as f of a colon semicolon epsilon. If f is continuous, the inverse image of this open ball is something very big or something like this. I name this set as inverse image of B of f of a semicolon epsilon. This is a bigger set. This will contain the open ball whose center is at A. So what happens is, this B of A will be inside the inverse image of this open ball. Okay. This is by the definition. This is the definition. Okay. So these all things is already we discussed in the previous section. Okay. So now, so that's what we are going to use this definition here. Since f is, this is in terms of open balls it is given. Okay. Now, so now we come to the theorem. This so this is an open ball. This is an open ball which is a subset of G. So now we are going to use this definition for this open ball. Hence, the inverse image of B of f of x colon semicolon r. We are going to use the definition. This inverse image of this open ball will contain the open ball shape with center at x and radius something delta we can take. This is r we have taken. So if we take r, I can put this one as delta. Do not use the same r. Okay. Okay. Now what we have to prove actually? We have to prove that FNS of G is open. So for that we took one element in FNS of G. Just now we proved that yes. Hence, by using this definition, we proved this one. FNS of this open ball will contain this open ball. But what about this? See, this is an open ball inside G, something like this, smaller one. Okay, like this. This is what is this open ball. Okay, so that is open ball inside G. So the inverse image of this open ball, this shaded portion is nothing but what? FNS of G. The entire G, if you take the inverse, this is that we get. So this one subset of this G. So if we take the inverse image of this open ball, it will be somewhere inside this. This is what we call it as F inverse of B of f of x colon semicolon r. And this contains what? B of x colon delta, somewhere here. But this is a subset of what? F inverse of G. So that's what I am going to finally write it. So hence, but F inverse of G contains F inverse of B of f of x semicolon r. Therefore F inverse of G contains the open ball B of x colon delta whenever x belongs to G. This implies that x is a general element. Therefore, F inverse of G is an open set in M1. Hence the necessary part. See, we are using this definition in terms of open balls. So, to be very careful to read many times so that you can understand the sequence of which space we are in and what is F inverse of G, whether it is in M1, M2, everything. Okay. So now we go to the sufficient part. That is, we are going to assume that whenever G is open in M1, M2, F inverse of G is open in M1, we are going to show that the function is continuous. So the function is continuous means it's continuous on the entire domain. So now we are going to assume that a function is continuous at a particular point. Since the particular point is an arbitrary, we can assume that we can say that the function is continuous in the entire metric space. So now we are going to assume that suppose fnus of G is open in M1 whenever G is open in M2. This is what we are going to assume for any open set G. We need to prove that the function f is continuous on M1. It is sufficient to show that f is continuous at an arbitrary point, say A belongs to M1. Now let us consider an open ball. I name that as script B. It's nothing but B of f of A semicolon epsilon. See, we are going to use this definition now. This is a definition now. So this definition. If inverse image of every open ball contains an open ball, then the function is continuous at that point. Okay, definitions are always if and only. See here. So this definition I am going to use. So I start with open ball. So that's why we start with open ball, not open set. Let B be an open ball, be any open ball about the point f of A. This is an open ball in M2. This is M1. Next, this is M2. I take one open ball, say like this, whose center is what? F of A, radius is epsilon. This open ball is nothing but B of f of A semicolon epsilon. For simplicity, we put this one as script B. Every time we don't want to write this f of A colon. So now what we assumed is inverse image of every open ball let us assume that this is an open ball in M2. By our assumption, what is our assumption? Inverse image of every open set in M1 is open in inverse image of an open set in M1 is open in M1 whenever G is open in M2. But already we know that every open ball is an open set. Therefore, I can use this one for this B. B is an open ball. Therefore, every open ball is an open set. Therefore, the script B is an open set in M2. So, by our assumption, this implies that fnus of this B is open in M1. Open in M1. And actually, what is B? This B is nothing but what? This is B of f of A semicolon the inverse image of this. So something like this. This will definitely contain what? A. Because f of A is the center of this. The inverse image of this will definitely contain A. Other than A, many elements are there. So that's why we put like this. So fnus of B, this is fnus of B. So fnus of B is open in M1. This is by our assumption. Since A is an element of fnus of B and fnus of this B is open. This implies that by using the definition of open set, it implies that there exists an open ball. There exists an open ball, say B, whose center is at A and radius something delta. Radius delta, that is contained inside what? Fns of B. This is the definition of open set. So we have assumed it. So again we are going to use this result again now. Now see what we have done is, in the sufficient part, we have assumed that Fns of G is open in M1 whenever G is open in M2. We have to prove that F is continuous. So we have to show that F is continuous in an arbitrary point. So now we take one open ball here, which is an open set. Open ball which is an open set. So the inverse image of this open set is somewhere here, this one. This is also open by our assumption. So B be any open ball about it. Therefore B is an open set, because every open ball is an open set. And Fns of B is open in M1 because of this assumption. Okay. So Fns of B is open is because of our assumption. And Fns of B contains A. Just now I explained why it contains A. Okay. It contains A and Fns of B is open. Therefore, what is the definition of open set? Says there exists an open ball whose center is at A, is completely inside Fns of B. So now what we proved here is, this is an open ball. This is an open ball. What is that open ball? Script B. The inverse image of this open ball, that is Fns of B, that contains another open ball whose center is at A. You please go and see this definition now here, section 5.3. The inverse image of any open ball f of A about f of A contains an open ball B of A colon delta. If this happens, then F is continuous at that point A. So that's what we are going to do it. Now, inverse image of this open ball, that is B F of A, it contains an open ball what? B of A colon semicolon delta. Therefore, by this implies that F is continuous at the point A. Since A is arbitrary, since the point A is arbitrary, the function F is continuous at all points in M1. That is, F is continuous on M1, and this completes the sufficient point. Let me see. Hence a sufficient part, and this completes the theorem. So this is very important theorem. Definitely these kind of questions will be asked in university exams. So students must practice a lot of times. So they want to understand, you can just draw like this and understand. Simply instead of memorizing, you cannot memorize these things. So this section 5.3, this is like a definition. It's very, very important for this thing. Thank you. This one here you can put the definition. This one is, you can put your own symbols. This is what. This one I used there. That implication is because of that definition. Because inverse image of open ball contains an open ball. So then it implies that F is continuous at that point A. Since A is arbitrary, F is continuous at all points in M1, and hence we simply can say that F is continuous on. Okay.